Pleased to introduce our presenter for today's training and webinar, Dr. Haselbach, PE. She is a professor and chair of Civil and Environmental Engineering at Lamar University. She authored the McGraw-Hill book, The Engineering Guide to Lead New Construction Sustainable Construction for Engineers, and served as the Associate Director of the U.S. University Transportation Center for Environmental Sustainable Transportation in Cold Climates. She has authored numerous papers on sustainability related to site issues, concrete, metal mitigation technologies, life cycle assessment, and low impact development. Her degrees are from Cornell, UC Berkeley, and she received her PhD in environmental engineering from the University of Connecticut. She's a licensed professional engineer and a lead AP, BD+C. Thank you for presenting today.
Hello, everyone.
You can take over.
Can you hear me? Mike, can you hear me?
Yes, we can hear you perfectly.
Okay, well,
yes, we can hear you.
Okay, thank you for coming to this presentation. I'm here at Lamar University with some of our branch members, so there might be a little bit of stuff going on in the background. So I have to do 2 screens at a time. So with this, I shall start. So the first thing I want to talk about is what the benefits of pervious concrete is. And this talk, I'm mainly going over things that I think are important for Texas, as Texas might eventually start adopting these technologies. So pervious concrete, a pervious concrete system, is considered a best management practice to reduce stormwater runoff. It can help in meeting your TMDL, your total maximum daily load targets for water quality. It allows for natural groundwater recharge, reduces the heat island effect, reduces ponding and icing. And some of the recent research that we have done here is surface infiltration on the top of it, clogging for the systems by run-on from other surfaces. The aggregate bed, you'll see later, there's the underground storage bed, how that drains down. We've looked into neighboring soil moisture and temperatures, impacts it might have if it was a shoulder. We've looked at heat island impacts. I've done a lot of work recently on de-icing chemical impacts, and then overall stormwater quantity and quality impacts. So with that, I want to tell you that these permeable pavements, not just pervious concrete, they're systems. And by the way, we have a pervious concrete patio here at the Lamar campus, almost installed by our senior design team last spring. And as of Saturday, we now have a permeable paver patio installed by a senior design team here on campus too. And there's systems in that they have both a structured surface that could be used for vehicle or transportation or parking, etc. And they're also a stormwater system. And the stormwater system is below, so you have a top layer of the pavement layer, and then you have aggregate storage beds below. And they come in many different shapes and forms. So people might say, well, how deep should this aggregate bed be? Well, first of all, there's structural considerations for loads of what kind of traffic you're going to have on it, because these permeable pavements, a lot of them are weaker than other pavements. And in addition, you have to figure out how much water you want to store based on your storm and the runoff and what you want the system to mitigate. So that could add a lot more depth. And then you have to consider whether you're going to just detain the water, like one of these shows here with that pipe on the bottom, or if you're going to retain the water, as in let the water actually have time to infiltrate into the ground, or partial for both. And then finally, there's frost depth issues. So if you are in an area that has a frost depth, you do not want the water to go in up to the frost depth, because then it will, when it freezes, it will break up the system. So you can also put permeable pavements on a slope. Remember, it's a system. And so this sketch here just shows how they put it on a slope. And with the slope, you don't want the water running on down and then out the bottom, because that would be sort of freaky to walk along your sidewalk and have water pouring out of it. So instead they put in internal dams, and I'm going to show you some that were put in. In this case, not only do they have the dams internally for infiltration, but you can see they have an overflow at the end of it that allows for on larger storms to go to an outlet in the stormwater system. There's also a caveat, is if you have it on too steep of a slope with a lot of runoff coming, the water can go so fast it will overshoot the system. So there's a lot of considerations for the systems. So what is pervious concrete itself? Basically, you take some rock, you take some cement or other cementitious material like fly ash, some admixtures to help it work it and all, and some water. But you carefully control the amount of water in cement to make this kind of paste that coats the aggregate particles. And the aggregates tend to be narrowly graded, so they're almost the same size. It's like stacking marbles in a jar. There's a lot of voids in between. But if you put in a lot of little rock and pebbles and all in between, you'd fill it up. Well, we don't usually do that. And I like to say it's more like dough versus batter, whereas normal concrete's more like batter. So typically, the porosity of pervious concrete can range from about 13%, so that's the voids in it. And less than that, you tend to have blocked the flow channels, and it can go up to 40%. However, at 40%, it's so weak, it breaks apart pretty easily under traffic flows. We try to design it for somewhere between 20 and 25% porosity. It's a very tortuous material, and you should know that it has both vertical and horizontal flows. If you look at the picture here, you see the one stream coming down, but just a few inches later, it's totally spread out. The compressive strength we don't use for specifying because it's very variable and it's not as strong as normal concrete, but typically it could be between 1,000 and 3,000 PSI. You can make it stronger with different things like adding fibers and stuff like that. But what they generally do is make it thicker so you can spread the vehicular loads down, and then you have the gravel underneath it before it eventually gets to the soil below. So how is it placed? So I've used this same picture since 2014. That's me in the bottom left there. That was when I was trained to put in pervious. And there's been a lot of improvements in the technology and the equipment used for it since then, but still it's a good picture. So I have the mixed design for traditional concrete there versus pervious concrete based on mass. So like 1 kilogram of cement. Well, with pervious concrete, you put in 4 to 5 maybe kilograms of rock. You use about 1/3 of a kilogram of water, and you typically don't use fines unless you want it stronger, so you can put in a few fines for it. And you can see, you just go to a normal concrete producer. It comes out of the chutes into your truck. You use a typical concrete truck, and when it comes out the chute, you sort of have to help it come down. You can walk right on it, just like roller compacted concrete. Your boots will not go in. Then you basically have to compress the top, so they do use rollers and all on it for different compaction. That makes the top denser, so it's more durable, less raveling, plus it keeps a lot of the dirt out. And then immediately cover it with plastic within 20 minutes, especially if it's a dry day or a windy day. And you staple on down the plastic and come back 7 days later and it's done. So these are some examples of some placements in Pullman, Washington. And I just want to tell you, when I went to Washington State University, they told me they couldn't use permeable pavement systems in Eastern Washington because the soils held water so much, and it was rain on snow events in the winter and all. And yet when I left, they had about 7 placements there, and they were very happy with it. One of the reasons they liked it, it wasn't so much that they had a lot of rain. It's an arid area with only 20 inches of rain a year. But that picture there on the right, you can see is there was very little black ice formed because melting snow during the day would go in instead of standing. It can ice over in ice storms, but you can see it reduces the black ice a lot with it. And you can use it for many applications, from sidewalks to roads. That bottom left picture is for their veterinary medical school, and that isn't the best application because that had a lot of trucks, big trucks with animals coming into the medical facilities there from all over the Pacific Northwest. And those snow plows would have to turn around on it and scrape it. So it was a pretty rough environment to put pervious concrete down. You have to be careful where you put it and be smart where you put it. There are times when you put it in a portion and not in other portions. So with that, let's talk about a few things that happens with pervious concrete. So when you first place pervious concrete, right when it's placed, the 7 days later, you can have surface infiltration rates at 2,000 inches per hour. So you think of Harvey at 60 inches in 3 days versus 2,000 inches per hour. But it rapidly clogs some. So the fines and all, the larger debris will catch on the top, and that needs to be cleaned periodically. And some of the finer material will go inside. So if you look at this graph here, it's 4 different locations on a sidewalk in front of the engineering building in Pullman, Washington. And as the time went on, you can see the infiltration rate drops tremendously. It drops in half, like every year. And if you look at the red and the blue lines, we were just following that. Eventually, they were getting down to about 50, 60 inches per hour. They were still functional. They were functioning fine because that handles the storm. Below that, you have to think of cleaning. So for the aqua and the green lines there, those were areas that received a lot of runoff from 100 feet or more of sidewalk up above it, that there would be a lot of things coming on down from. And so that they rapidly clogged for those 5-6 feet there, and their infiltration rate became so that it wasn't functional for handling stormwater. The water would just bypass it and go to the next section. So what we did, we took hoses out there, we power washed the top, got some debris, swept it off, and you can see to the right then that we regained enough infiltration rate for it to be functional again. That infiltration rate that you get after cleaning will never ever get up to that initial rate. But after cleaning, they find it gets up to rates up to 500 inches per hour, depending on your cleaning, which is more than fine for any storm we'll ever have. So this is an interesting thing. In order for us to determine what was happening there, we used an ASTM test C1701. It's a surface infiltration. It's a single ring infiltrometer, very simple, a single ring and about 12 inches wide, and you just plumber putty it down, and you use 5 gallons of water, and you see how fast it goes in. But we were doing it in the same place all the time, and after a while we realized that as we were putting this extra load of water on, we were actually taking some of the silt and pounding it deeper in and reducing the infiltration rate. So I've learned that you need to do infiltration rates randomly now. And just let me tell you this, that on the exact same placement, put exactly the same way, and if you go 10 different places on it, you will get infiltration rates that vary by 30, 40, 50%. It's okay. There's a huge variability in the infiltration rates, just depending on the flow paths and whether someone stepped in that location or not. But as long as it functions, it functions. So let's talk about how you place it. So this is a sidewalk put in Pullman, Washington, and I wanted to show you this placement because it has the dam we can see in it. So we basically had a slope sidewalk, and we wanted to do some testing on it and research on it. Plus, we wanted to make sure we didn't overshoot with the slope. So we had an upper aggregate bed and a lower one, and the yellow you see there is an impermeable membrane that we put down over the dam. That dam happens to be an earthen dam. The soils there in Pullman, Washington are the famous silt loams that hold water so well that the winter rains produce the best wheat in the country with no summer rain and no irrigation. So anyway, you almost can cut it with a saw. So we covered that dam, and then on the right, that's a permeable fabric that's down there, and we tend to line it with that so that the soils below don't go in and start clogging the system and things like that. So you can see from it that we have the closer to you is the upper bed, and then it goes over the dam to the lower bed. All right, so then they filled the beds with gravel, and the gravel for the aggregate beds can be many different sizes. You can use larger or smaller. It's just that near the top, it's good not to use aggregate about more than 1 inch in diameter average, because otherwise a big rock would stick up into your concrete placement on the top. So you can put larger below and then a thinner layer of the smaller on top, or whatever's available. You can see right behind the sign there's an observation well, and on that bottom right corner, another observation well we did some testing on. Then to the right, you can see them placing the pervious concrete. It almost, as I said, looks like roller compacted concrete. And they're swiping it off and raking it even, and then they rolled it. And we can see that on the next slide. In this case, since it was such a small sidewalk, they used one of these small hand rollers. Typically, they have larger ones and ones that vibrate and all for it. And then there's some, manufacturers have made some specific equipment to even make it better now. Again, it's important to compact the top for strength, durability, and to keep the soils and all from going out of the system. Behind the two gentlemen there to the left, you'll see these things look like a pizza pie cutter, and they made a small little groove on the sidewalk, so it looks like they have cut the sidewalk all the way through, but they haven't. Sometimes they go back, the day after, and they'll use a saw cut instead. This helps with the surface, but you have to be really careful with it doesn't start raveling there. So what they did then was they put the plastic on it, and it was done in 7 days. So what did we find out from this sidewalk? This is a elevation view of it, where to the right you can see the upper bed and you see the dam, and then the lower bed, so that you can see it's an aggregate bed and it's a pervious concrete layer on the top. They happen to have a 6-inch thick pervious concrete layer, which is pretty thick for a sidewalk, but it just so happens that in Pullman, Washington, their sidewalks are designed for various vehicles to ride on it, for snow plowing and other reasons. So they use the same type of depth you might use for a parking lot. And then you can see that there's a good 2.5 feet of aggregate storage bed. There's a lot of water to store. Plus, we also didn't want it to go up to the top. They don't have as much rain in Pullman, Washington, so this bed was designed to never fill even on the worst rain or snow melt events. These are plan views of it, and the upper left one shows we did a lot of censoring for the moisture nearby. That's because some of the DOTs wanted to know, well, if we put it as a shoulder next to a highway, is the moisture going to go into our main line and then cause damage there? The data we found showed that that's highly unlikely. But most of the research on that hasn't been finalized yet. But what I wanted to show you was the bottom right one. If you see that one bed to the right has a monitoring well, and then the bed to the left has the monitoring well for it. And what I have been asked to respond to a lot in Texas is, okay, these underground beds, are they actually going to infiltrate with the soils we have? Remember, I'm on the Palouse silt loam here, and I'm in Beaumont, which has soils that, crawfish and rice fields are on. So you can imagine that they hold water, just like a swimming pool. Anyway, so we have these two monitoring wells, and we did what I call drain down studies to show how fast it will infiltrate. So the first thing was we had a big truck of water come, and it filled the upper bed. So if we look at this diagram here, the upper bed is zone C, which is in the black, and we started filling up that bed. And then it levels off because it starts going over the dam. And it goes over the dam and starts filling up the lower bed, which is zone A in the gray. And as soon as the lower bed started filling up, and it reached the same about 22 inches, we stopped the flow of water and we allowed the drain down. So then you see the curved line in black as the water started infiltrating into the ground, And again, it's only infiltrating in the bottom and the 3 sides. And we see the gray line for the other zone, and they're identical. What's important about this is you can always say, well, maybe it's draining because there was a root there and has a channel to some other flow channel. But we were very careful with these beds to make sure that things like that weren't there. And since they're identical, it sort of shows that this is actually the infiltration rate of that soil there. So we allowed them to drain, and when the upper bed, zone C, was about halfway drained, we filled it up again to see what happens. Well, after it's really wet, is it still going to drain the same? And then you can see we filled it to the top, and it's draining the same. So the infiltration rates are really good. We took bets on it before we started because we were in soils that they say this wouldn't work on. And we were betting, 2 days, 2 weeks for this to drain, and it was 2 hours. So we were pretty pleased with that. So what about here in Beaumont, some of the worst clay soils you can imagine in the state of Texas? And you can see what it's like at our community garden where our students put the patio in. This is standing water that was there last spring in April. And frankly, is the standing water that's been there a lot the entire last year and this weekend and these days. So you can see the standing water. Well, we installed this patio so it was up above the natural grade. We call that a standalone pervious concrete system. It's not taking water from other things above it. A hybrid system is where it might have a sidewalk running onto it or part of a parking lot running onto it. It is not a good idea to have a landscape bed run onto it because then you're just going to clog it with dirt all the time. Or put dirt and stack other things like dirty snow on it. So anyway, this was a day, as you can see the picture, we had standing water nearby, and the bed was raised, the top of the pervious, so at least a foot higher than the surrounding grade, and then they had a 2 foot deep aggregate bed. So we used the hoses because it's a community garden, and you can see there that we filled up the bed. And when we first filled it up, because the bed was raised, it also had some aggregate on the side of it. We would call it daylighting on a highway a little bit because they dug the hole a little big and they had a little extra aggregate on the side. So the first part of when we stopped filling it, draining down, was when it was flowing out these side sections, or what we would call daylighting of a system. And after that, we just let it drain naturally in these soils. So you can tell how saturated these soils are. And you can see it draining down. So in a day's time, it basically drained the 9 inches or so that we expected it to. It drained down to standing water in the underground aggregate bed. That standing water represented the groundwater table that was there. So those 9 inches above the groundwater table there were able to drain in just 1 day. We have repeated that test this year. I take that back. The one you see here, I believe, was done in July, and we just repeated it April, and it took a few extra days. The initial drain down was pretty good, but then it got slower and slower, and we're not sure. We're doing further investigations onto why that happens. We think it may have to do with the fact that this first one was done during a very hot time. So there was evaporation going on around with the groundwater table going down too, which helped the draining, whereas the one here in April, it's been very, very wet and it's not nearly as hot, and we didn't have those additional mechanisms helping those last final inches drain on down. But the good news is that, yeah, you can use this in the Beaumont clay soils in Beaumont, Texas. There's a director of public works of a large city in Texas that says, oh, we can't use those systems there because they won't drain. If you can use it in Beaumont, you can basically, if it's designed correctly, use it about anywhere. Will it handle a Harvey? No, it's not intended to have a Harvey. It's intended to handle the rains that we seem to have every month here that cause all the flooding and concerns on the roadways. And during those huge events, it obviously, the whole system will fill up to the top. And that's one thing we're interested in seeing is after some of these huge events, how much does that impact the system also? So I wanted to let you know a few other things. So we have that surface infiltration test, And people always ask, well, how porous is the placement you've put there? And they have to go out and they have to core some samples and send it to a testing lab and do the porosity test, which is also an ASTM test. But as practitioners that have seen many of these placements, we just throw a bucket of water, and by how fast it goes, we sort of know how porous the placement is or not. So this was a study using, a lot of different sample specimens we made in the lab and little slabs that we made. A lot of them, in fact, all of them that you see there were done in Brazil. And we basically would do the porosity of it versus the initial fresh infiltration rate. And there's a pretty good correlation. So if something's down to only about 15% porosity, that initial infiltration rate is down to, maybe 500 inches per hour. But when you're in the range between about 20 and 25% porosity, you have a really good initial infiltration rate of somewhere about 1,500 to 2,000 inches per hour, which is really nice. You don't want to go too far if you have a really fast infiltration rate, above 2,500 inches per hour, then you probably have a pretty porous placement, which might not be as durable. So it's a good way to have a quick idea, and you can do it all over your slab without doing a lot of cores. So this was sort of a rule of thumb kind of exercise we did. We also did a whole bunch of deicer studies because it just so happened that there was a bad winter about 4 or 5 years ago in Pennsylvania, and a few of the placements, when they plowed the snow away in the spring, they were gravel again. So they didn't know which of the deicers it was, and people speculate, and there's been lots of studies on normal concrete. If you put the little white calcium chloride deicers on a concrete walkway and all, that you'll see some raveling and some degradation from it. We wanted to see, was it magnesium chloride or calcium chloride? And there's also could be a lot of impacts from what we call freeze thaw. So in other words, you could have these chemicals go in and fill some of the holes, and then we would have freeze thaw action going on. And sometimes it depends on what temperature the deicers control the water icing conditions to. But we studied only the chemical effects on. Why? Is because I'm an environmental engineer and I deal with the water side chemistry, not so much the material side chemistry. And you can read this later, but basically concrete, when you add the water to the cement, you get a lot of hydroxides. But from the air, it can carbonate and turn back into the limestone or calcium carbonate or different carbonate compounds that Mother Nature made naturally in our world. So it just so happens that in some aquatic chemistry, we have found that hydroxides prefer magnesium over calcium. So we wondered if the magnesium chlorides would strip the calcium out of it. But it just so happens that if it's carbonated, which means after a year or so, their surfaces are more carbonated from the carbon dioxide in the air, it seems to have less of an impact. And that might be because the calcium and the magnesium are about the same preference for the carbonates. We didn't think calcium would be a problem at all because you're putting calcium in a calcium system. Why would that be a problem? But it just so happens that we have a really super saturated calcium solution, which you would have if you put some calcium chloride deicer down and some of the water evaporates. It forms this very unique aqueous compound, which is a calcium hydroxide with one hydroxide in it, which is very hard to form, but when it does, it's stable. And we found out from our studies that the calcium actually degraded it very bad, and you'll see. These are the different constants that we used for it. If you look at calcium with the hydroxide, the single hydroxides, well, the calcium column under the hydroxide that has that 2 in the subscript, that's the calcium hydroxide preference, that 5. And when you go down to the magnesium one with the 2, it's 11. Well, these are order of magnitudes different. So it's 6 order of magnitudes preference for the magnesium or the calcium, whereas it's much more even, as I said before, for the carbonates. So we hadn't expected that. But that in the calcium hydroxide cell there, that calcium with the L next to it, that's that weird complex that only forms under supersaturated conditions, which with the pervious concrete, you have the deicer inside of it, and you have the water evaporating, and you're forming this odd condition that apparently strips it. So we also wanted to set up a protocol for testing in the lab for all different degradation things, and we made a protocol. We didn't know would it go faster in a hot room, which is a laboratory, or a cold room, which means you have to have a special cold laboratory for it. As we thought that it would be degrading more under fresh specimens versus more carbonated fresh specimens. We did some side tests on whether you added fly ash or not, and we did a few durability strength tests on this initial testing we did. This shows our method. We made the specimens. We placed 3% deicer solutions on them, calcium chloride, mag chloride, normal rock salt, and then tap water for a 4-month period. Once a week, we let it dry some during the week, as if you were having a snowstorm, and put deicers down every week for an entire long winter. We consider it a very extreme winter event, like might happen as it did in Pennsylvania. And this was our results. The ones where we put the calcium chloride on there, we have 4 specimens. It actually started to just fall apart in front of our eyes. Whereas the ones with the water, the sodium chloride and the mag chloride really didn't. There wasn't as much of an impact in the cold room, which are the bottom 2 rows there. That C in the beginning meant the cold room. So in other words, the reaction doesn't go as fast under cold conditions. It was worse under the hot conditions, and you can see what was happening there. So then we came to Texas, and instead of using the basalt aggregate that we had used, because that's the most readily available out west, whereas it's granite more in the East Coast, we used limestone. And we did the same test. And what I want to show you here is what happened using limestone aggregate in our pervious concrete. That upper left one is after we did this test on 10 specimens that got calcium chloride. The middle is from 10 specimens that we had with limestone in it that we put water on. And to the right was the 4 that was the basalt. So if you looked at the left and the right, the one to the right is only 4, the one to the left is 10 specimens. But you can see that when we had limestone in there, it totally fell apart compared to it was bad enough when we had the basalt rock in it and degraded it. So the results of this is that the National Ready Mix Concrete Association has basically said, never make your pervious concrete out of limestone and put calcium carbonate on it. It will fall apart. Internally under those conditions. Obviously, someone puts a little bit down, it's not going to make an impact. But if it receives treatment regularly over long periods of time, it's going to fall apart. So what are we doing with mag chloride? The mag chloride seems to hold up better. And what we're exploring with here is some pre-treatments. We think if we can accelerate the carbonation, we may be able to limit the deicer impact so that people can be pretty comfortable about putting mag chloride down. But those tests are still in progress, so stay tuned for them. I also wanted to tell you about the heat island impact. So a pervious concrete, this was done down in southern Brazil in a midday sun, and you can see the temperatures. Those top 3 curves are the surface of it, and then we had thermometers halfway through, and then at the bottom of the actual concrete itself, not in the bed below. And the surface temperatures of pervious concrete, we've done a lot of studies on it, can get to about 140 degrees Fahrenheit. It's like walking on asphalt. And you go, wow, why would it do that? Especially it's a lighter color. It's because the heat cannot get into the system because it has all the voids. It's like a double pane window with the air gap in between. So that heat from the sun just stays on that really top layer there. So what we did was, other people have said, well, that's nice, you're preventing getting into the ground, but what happens if right of a sudden water goes into the system? You have to understand that it could rain in the middle of a really hot day, so we mimicked that. And the orange line on the top was one of the slabs there that didn't get water, and the blue and the silver ones are ones where we put in approximately about a centimeter of water, just about enough water that would just bring the would go through the top layer and not get into the aggregate bed before. We wanted to see what happened. You can see an unbelievable drop in the surface temperature. That water we put on it, just like a sun shower, pulled that heat into the system. And then the middle lines there are the ones what happened to the inside. You can see in the middle of it, the temperature rose a lot. Way near the bottom, just a little. The good news is that afterwards, we let the system be as the day went on. The evaporation that came from the system helped to balance that heat that we actually brought into the system to take it out again. So it's a pretty complex physics problem to deal with the heat and the rain and everything else at the same time with it, because it's not just a surface phenomenon anymore. We have a system where we can actually flow hot water in or flow cold water in. Pretty unique. All right, so these last two slides that I would like to show here have to do with water quality. And everyone knows that, you know, total suspended solids is really important. And these systems here, because they decrease the amount of stormwater runoff, will help decrease the amount of total suspended solids and erosion you have downstream because you have much smaller flows. We also know that if it's going into the system, some of these debris and dirt will be on the top, which will periodically need to be cleaned. When I was in Washington State, zinc and copper are two big issues because salmon is king in the Pacific Northwest, and it just so happens that some of these metals, if they're above the background levels that we normally find in normal soils and in normal water systems, could affect the young fry or some aquatic species. So we did some experiments, we call them hotspot tests. These are with parts per billion we have here on the y-axis. And for zinc in background stormwater, you know, it's about 50 parts per billion. So we pretended we were at a place, for instance, a place where you had a lot of tires, like right on the side of the road where a lot of that stuff would come. But also just think of this, around any facility that has galvanized fencing, that galvanized fencing will really bring up the zinc levels. And we poured it into one of these specimens. And I just want to tell you that when we pour the water in the specimen, it comes out of the bottom within a minute. And within a minute's time, this is what happens. That's what we call tertiary treatment in the United States. Oops, it sort of went below this computer here. It's supposed to end up on that bottom line. So we brought it down to background levels that you would normally have in soils and all. And so it was more than 95% reduction in that amount of time. And then people go, oh, but it's gonna eventually, you know, be full of zinc. No, we're talking parts per billion in stormwater versus a gigantic slab of concrete with tons of concrete. It would take our lifetime before we ever went and had a breakthrough with the zinc. So then we went to copper. And here, the background for copper is less. It's usually about the 10 parts per billion. And again, it's not so much an example for Texas. The zinc is a better example. And why I brought this in now is because I spent some time at lunch with some of the people at the Porto Beaumont, and their stormwater, they consider zinc because you just imagine that this fencing that they have is right on the edge of the water. So pervious concrete is a good option for having around the perimeters of these facilities to have tertiary treatment done without even putting in a fancy treatment system. But for the places where copper is important, we again poured the water in less than a minute, comes out the bottom. And again, my little bar went a little too low, but it went back to a tertiary treatment in just a minute. And again, you have so many tons of concrete versus parts per billion of copper that it would last for our lifetime. About a 90% average reduction. And what was interesting with the copper, as time went on, because we kept doing this again and again and again, and we mimicked like 15 years of time for it for the Washington State DOT's information and other agencies out west, it got better. It started removing it better after we mimicked 5-10 years of stormwater runoff going on it. So with that, I'd like to entertain questions. I leave this one slide up for your viewing because I want you to know that in Beaumont, Texas, we can put in standalone systems raised a little bit above the groundwater table, and we can actually have it infiltrate in a period of time that's reasonable. So Mike, if there's any questions, or Kimberly?
Nobody has submitted a question at this time. Does anyone have a question? You have to just type it into your little chat bar.
I'll do you after. I do have a question here from my audience.
Okay.
So what's your question?
When you're doing roadway sections, you need to include expansion joints like you would with normal concrete road sections?
So we have a question here of whether you would need expansion joints for roadway sections. And I know that they're experimenting with that at the University of Sao Paulo in Brazil. So first of all, I'm not proposing to use this on main highways, but they have used it for lots of side streets around the country. And they don't think they need the typical expansion joints that you would use for, you know, cold and hot, expands with hot and all, because that it has so many holes in it that it has room to expand just within its own section. The joints they put in it are just because no one's fully proven that they still do some joints in it for comfort level, and you know, you don't want to put a placement, but they really think that the full depth joints are definitely not needed on the sidewalks. And there are some studies on whether it's needed at all on more roadway sections, which are much thicker. By the way, just so you know, pervious concrete, if it's going to be just for a sidewalk without vehicles on, is usually about 4-inch. Parking lots about 6-inch depth. Small side streets and all about 8-inch. And you can go up to about 12 inches in depth. You can't go beyond that because it has to be done in a single lift. If you do it in more than one lift, you could have internal clogging, which would be hard to clean and mitigate for later on. And the 12-inch ones, they've put on actual concrete plants for the loaded concrete trucks to go over. And we've done studies on them functioning well after many years. So were there any other questions?
I don't have any questions in the chat bar. Anybody have a question?
About the pressure washing you use on.
You did a great job.
Wait, I
Nobody
have
has
one more
questions.
question here about cleaning.
Okay.
I'm prepared for this because always people say, how do you clean it? And I say, well, you can pressure wash it. So I can pull ahead another slide here. So this happens to be a gigantic parking lot they put in Pullman, Washington. And it just so happened that most of it stayed really functional, but this one corner here happened to have a gravel parking lot upslope from it, which ran on and visibly clogged it. You could see it was packed with the dirt for it. We had first tried on some other locations to use like a dry vac, and the dry vac did nothing. A dry vac works well if it's at a beach with nothing but sand, but when you have these clayey type soils, they're sort of baked in like a lasagna pan. And it doesn't work with just a dry vac. So what we did is we wetted this area that was clogged so that it would get a little bit softer. And then they just used ditch witch, which the university happened to have for making ditches. And they power washed and vacuumed it up. You can see at the right there on the top, all that debris we got up from this small, you know, like 5 foot by 5 foot section of all the debris that went in it. They vacuumed it up, and that bottom picture is 5 gallons of water going in within 30 seconds afterwards. So keeping some of the debris like leaves off of it so that doesn't get impacted in is good. Vacuuming on sand is fine, but you really have to power wash if you're going to have the more clayey soils.
But you have to, when you power wash, you have to suck it up. I mean, are you power washing and sucking up at the same time? It has to be done like that?
So they asked if you power wash, you have to suck it up at the same time when you're doing it. In this example, we showed that on our sidewalk, when I just did it with the hose, we let it go into the landscape bed. The issue has to do then with the dirty water. You can't wash that dirty water into a storm sewer. So yes, if you have a storm sewer nearby, you have to vacuum it up. But if it's just the dirt from a landscape bed and you wash it back in, most of the different departments of environmental conservation or environmental quality, et cetera, fine, I think that's fine. But if you're on a paved area and there's storm drains there, you know, they don't want you washing the power washed stuff into the storm drain.
But do you wind up power washing deeper into the system?
So again, we're getting more questions, but I told you the washing is, the question is, are we power washing deeper into the systems? We are in some sense, but if you look at that hose there, it's at an angle, and you can see that that top like centimeter has all the clogged stuff and it's coming up. So there'll be fine silt that goes all the way through the system, but most of the things that is going to make this system not be functional for its 30 or whatever year life are going to be picked up by the power washing at an angle like that on the top. All right, I think my audience here is done with questions, so we're done.
I think we have one more question that has come in while you were answering that one. And the question is there any recommendation on a design manual or best practice books for pervious concrete?
So ASCE has done an entire book on permeable pavement systems. And then there are manuals, like for instance, the interlocking paver ones. The ICPI has a whole manual on that. The things that's recommended, and then the National Ready Mix Concrete Association has these, they call it Pervious in Practice, PIPs. You can download, I've been part of the committee that nationally has been giving these recommendations on what to do or what not to do, like not using calcium fluoride on it with the limestone and that kind of things for it. So you can get a lot of information that way. The one thing is you have to understand is you have to pair up with a hydrologist or a stormwater person to figure out the whole stormwater system of it too. And every place you go, you have entirely different stormwater needs. So it's not that one size can fit all because the application. So it does take a bit of training for it, but I know that TxDOT's interested in slowly starting to get some standards in the state, and there are several standards for testing. ASTM has them, and ISO also, for us for acceptance testing, for infiltration rates to core, and then do the porosity, etc. Plus ACI actually has a specification, and it has a manual that you can get. So there are some good materials to be had.
Okay. I think that answered that. And I don't have any other questions.
All right, well, everybody have a wonderful week.